Hello all. So in last lecture, we stopped where we discussed a bit about using the return statement here. We didn't go into the detail, but in this lecture, we will start with this, that what's the role of a return statement? Are we able to save something using this return statement? And then we will move to conditional recursion, and also we will check our space and time complexity, which is the most important topic. So let's begin. So firstly, let's not use the return statement. And it's the same test cases that I'm using as a previous video, and let's say I'm not breaching. So since you will guess that since I'm not breaching, we will go to all the nodes. You can see 10 is up, then down. So we'll start from here, come to left, left, left. Then both none of left will be checked. We'll hit the base case, go to here, like left, root, then right. So 10, firstly 10, both calls are done. So 10 is up and 10 is down. Then we'll go to root, is 25. And then we'll go to 30. Both its calls are done. So it will be 30 is up, 30 is down. And then we will again go back to 25, which is, then we'll say 25 is down. Okay. And then after this entire thing is done, we'll go to 50. So that's how it goes. Correct. So like not going into much detail because this we have discussed already, and I have also told you to write it. So this is where this is the case where we are not breaching, and this is the case where we are breaching. Okay, we know that we are breaching here, that this 4 should be greater than 5, but still, even if we are breaching, we are checking everything from all the way up till 6. You can see that. So can return save something? That is what we have to see. So let's put return here, that when we are breaching, this is the condition where we have a breach, right? So when we are breaching, let's see what happens. You can see we are not going all the way to 6. 6 is not even checked now. So we are saving something, right? And similarly in this case, right? When let's breach, because if we don't breach, then it will go all the way everywhere, right? So let's breach firstly this case. Let's again breach the same. Let's write 75 here. Let's run it. Now it's breached. So it won't be true. It will be false. Yes. But here as well, we are going all the way until 100. I mean, everything, right? We are, even though we are breaching here, we are going everywhere, like, and then 200, then again coming back. So we are going all the way until 200. Why? Okay, so let's try to see that. Let's try to see that in the smaller example. You will get why it's happening in the bigger example. But just let me show you what's changing in the bigger example when we are breaching. Here, 30 is never down. If you will check by going back into the video, that when I use return statement, then 30 is just up, but it's not down. So we are saving some calls. You can see here as well. So it's not like when we are breaching, we are not saving. We are saving. Okay, but something. Okay, and why this happens will be clear if we'll see this. Okay, because this is the smallest. So let's try to see that in the whiteboard. Let's try to dry run. Will take a while, but I think it's worth to dry run because since we are in the initial lectures of recursion. So firstly, let me write the same code here as well. That here it's the condition that if my oops, if my previous is not equals to none, and my just I didn't write self dot previous, pardon for that. And if my previous is greater than root, of course, dot value, previous dot value and root dot value, greater than or either even equals to, it's not allowed, then what we will do, of course, we will set our flag to false. So our self dot is valid will be false. And here we are returning. Let me write in bold. It's not in bold, but just to grab our attention there. It's right. So because we are discussing the role of this return. And of course, there is one more thing that should be there. Let me write that we have to assign previous. I have to write that again, but I will. So now my self dot previous, here I wrote self, I hope you will understand, will be root. So then let's write self here as well. Oops. This is self. I hope things will be fine. And also it will be self. Okay, doesn't matter much. I have written. And now what should be there? Our write call in order, root dot write call should be there. What else? Just our print statement, pop the root's value and it's down. Okay, so let's try to dry run. Here is the same example of case 2 from our Leetcode. Okay, so that we can dry run. So I have just written this before recording. So we will start from here. Root value, we'll check the base condition. No, it's not satisfied. We'll go to left. So we will go to here. So firstly, what will be executed? Our in order 5 will be executed. This is a node. Okay. So firstly 5 will be executed, but it will hit root dot left, which is the same function calling itself. So we will again call the same function. We'll check again the base condition. No, it's not satisfied because left side is 1. And we are again hitting root dot left. So firstly, what is going on right now is in order of 1, and what when we were executing 1, we are again hitting 1 dot left, which is none. So now our stack will have none. This is our stack. Okay, so people also call it recursive stack, but we'll call it stack. So now we will hit the base case, correct? So since the base case is hit, so we will return, and it will return where? Because it was the left call, because we are checking the left none. It was a left call, so we will return here and we will move further. So what will be printed? Root. Firstly, since we are returning, most important that the return statement, there is a popping that happens on the stack. So none is done, and now our root is 1 because whatever is on the top of the root, or sorry, top of the stack is root right now. Okay, so what is root dot val? 1 is our value, and we will print 1 is out. Okay, right now our previous is none because we have initialized it, so this condition is not checked, we will not go inside, but now our previous will be updated. So let me keep track of previous here. Again, let's write self. I'm a bit lazy writing self. Previous is right now 1. Okay, so our previous is now updated, it's not none anymore. Now we are going to root dot write. Root is our 1. 1 dot write is also none, right? Both are null null or none in Python. So again we will hit the base case and we will return. So firstly the steps will happen. Again, I'm not writing properly, but quickly. Firstly, none will be there. We'll hit the base case. So we will pop this out. Whenever return happens, we have to pop, okay, from the stack. So we will pop and we will return here, right? Because it was the right call. This was the right call. This none was the right call of. So we'll return here. We will move further and we will see what will be printed. 1 is down. So we'll print 1 is down. Now entire both sides of 1 are done, right? So we will move back to 5. And since both the sides of 1 are done, we can now pop it out. Okay, because both sides are done. So we will move back to 5. So over to 5. Now the root is 5. Okay. Now what will happen? Since 1 was the left call, right, of 5. So we will return here. Mind it. Now we will return here. So we will go further. What will be printed? 5. So we will print 5 is up. We will check the condition. What's previous? Previous is 1. Is 1 greater than 5? No. Still we are not hitting this condition. So we will move further. Now my previous will be updated to root, which is 5. So I am updating my previous to 5. Again, we will go to root dot write, which is 5 dot write, which is 4. So what will be called in order of 4? 4 will be called. So we will again go back and check, is 4 none? No, it's not. So Now again, 4's left, okay, because right now it's 4, our root is 4, so root dot left, 4's left is 3. So in order of 3 again, correct. Again we will check, it's 3 none, no. We will again come back here and we will check 3's left. 3's left is none, yes, we are hitting the base case. And as I said, when we hit the base case, firstly again this will happen, that in order of none will be there, this is the left none. Since we are returning, we will pop it, so it will be popped, okay. And again our, and where we will return, we will return here on the left, because this was the left none, correct. So we will go further now. Since we have returned, what we will write, 3, so we will write 3 is up. Now we will check what's previous. Previous is 5. Firstly 3, previous is 5, it's not none, so this first condition is satisfied. And we will also check 5 is greater than or equals to 3, because right now our root is 3, yes it is, correct. So we'll hit here, okay, and then we will return. So you may notice that even though with our eyes we can first spot this thing, that right side is 4, right, and that's why it's not a valid binary search tree, but programmatically this and this 3 and 5 will make this false, okay. So this just to check, just to let you know that, because why this happens, because the way we are using in order traversal, like left, root and right. So firstly left will be checked, okay. So we'll hit this condition. The important thing is now we are hitting to our main statement return. So what will happen, since we are hitting to return, and as I said, return will return to the place from where it was called, okay. So from where it was called, do you remember that from where it was called, this function? Since this was the left call, this none, because after this none was done, we finished this. And from where this 3 was called, 3 was called from 4, so we will return to 4, correct. So we will return back without going to here down anywhere. We will return back to this, because this 3 was the left call of 4, and now 3 will be popped out without doing the right call. Mind you, we are not doing the right call, because even on the left call only we are, when going further, right. So 3 will be up but will be never down, okay, because this condition is true. Then that's why we are hitting this return statement. And so what will happen is that we will return here at this place on the left call. So firstly let's pop out, because we hit the return and both calls of 3 are done. So firstly we have to pop out, so we will pop 3 without its third, okay. So 3 is up but it's never down, so both calls of third 3 are not done. That's what this indicate, up and down. If it's down then both calls are done, but 3 is just up but it's not down. You can verify it here as well, that 3 is up but it's never down. You can see after 5 3 is up but it's not going to be down. Similarly, let's move further now over to 4, right. The control is here now, so what we will write, 4 is up. We will move further, next statement. We will again check that my previous, which is still 5, we can't update because we returned, right. We returned from here, so we can't update our previous will still remain 5. So again 5 and current root is 4 and 5 is greater than 4, this condition is satisfied. So again we will hit return. Again this will be false, but it's already made false previously, so it will be again made false, doesn't matter. So again we will hit return. So what will happen, we will return to the place from where it was called. What was running, 4 was running, and we will return back, okay, without doing the right side of the 4. So 4 will also be up but it will never be down. So you can see that here that we never printed, sorry, so you can see here that we never printed 4 is down, correct? And now everything is over to 5, correct? And 5, from where we will start? It was the right call. 4 was the right call of 5. So we will start from here. And what we'll write? 5 is down. So both calls of 5 are done. We'll write 5 is down. And we are done. So you can see, you can verify that 1 up, down, 5 is up, 3 is up, 4 is up, and 5 is down. And that's what we got. Correct? Now you can verify the same for the first case, which is the bigger case. And it will be easy now, as I already showed you that we will not hit 30 down. Why? Because it's breaching here. So we'll return directly. But after returning, it will go all the way. It's the same thing here. Even though we found the breach here only, right? We still went all the way. Why to go all the way again? We will go. Why? Because our recursion was not empty. Recursion stack was not empty. I forgot to pop because even when 5 is down, stack is empty. And after this, we are done. So until, as I said in the last class as well, and I'll highlight that again, that until the stack is not empty, in it means in the stack, until the stack is not empty, we will continue the recursion. And that's the reason we are going all the way, correct? That until stack is not empty, we went. So here as well, since we started filling stack from 100, 50, 35, 20, so we will go back, okay? And since nothing, there was no return, so we went here. This over, nothing is breached except this 2 places, right? So we will go everywhere all the way, and that's the reason we are going all the way. So what can we do? So firstly, I hope the role of the return statement is clear now. Now let's put that return, but in order to stop there, what can we do? So that's where we can say we can use conditional recursion, that whenever my self.isValid is made false by somewhere, we will not hit the right side. For example, if it's breached here, we will not go further. Okay, so let's try to do that. It will be better. So self.isValid. So only when this is true, then only do the right recursion call. Okay, so let's see any difference that we get. Okay, I forgot to call it. So what we get now? See, let's check the same case so that it's more clear. It's the same here. It doesn't change much, that we are breaching and we are going all the way, because here as well it's breaching. Here we are breaching at 2 places, 3, 5 and 4, 5, right? So it's the same that we got in our without using that. But here, if you will notice, after this breach has happened, okay, we are not calling the entire right side. You can see after this 35 is up and then 35 is down, that both calls of 35 are done. 30 is just up, it won't be down because right call won't be there, as I explained. You can see it's just up. After that, flow will be to 35 back and then 50, and then 50 will be down because we will not check the right side. That's what we have written, that if we are already false, then we will not check the right side. Okay, and that's why this is happening, that we are not checking the entire right side, so we are just going back. So, and as I said, whatever is gone inside the stack must come out, and that's why we have this, that 100 is up and 100 is down. Okay, because we started from putting 100 into stack, then 50, 35, then 10, then both calls of 10 are done, and then we went to 35, right? And then 30, then both calls are not done for 30 here because it's breaching here, but that's how the flow works. So that's the reason of using this conditional recursion. Now you might wonder, what if I also write the same thing here? That if somewhere on the right side, if it's false, then don't do the left. And let's check what happens. See, same thing. And also here, the same thing. But let's breach somewhere on the right side. Okay, so where we will breach? Let's try to breach somewhere on the right side. Let's take this as 45. Okay, instead of 75, let's have 45. And let's make this back again to true. Okay, and let's check what happens. Perfect. So we will check this 10, 30 will be checked, 30 up, down, 25, 50 will be up, will hit here, and then we'll go back here. Here 60 is both will be checked because previous will be still 50 for this. Okay, so it will still be valid. But after that, when we come here, this won't be valid. So 45 will be up and we will hit that condition of return. So we will return to 50 and then we'll return to 100. And then since we have written both the conditions, correct? We will not check the entire this. Let's remove this condition. Let's try to play a bit. Let's try to remove this thing. Then it should go all the way to 180 and 120s and 100s and everything. Check that. Yes, it is correct. So then it will go. But if we'll write this, then it won't go. Correct. And let's breach on both the sides. What happens? Let's see. And I don't know. I'm playing with it. And we have written both. Okay, left and right both. What will happen? Yeah, pretty less. If we are breaching here, okay, let's not put this and check, are we saving something? Yes, I think 10, 10, 35, 35, 35 is up. Then we'll go to going to 30 and then 35 is down. Yeah, that makes sense. Then 50, we are not checking the right, and then we are going all the way back. Okay, yeah, I think it doesn't change much if we write both 30 and yeah, it doesn't change much or nothing is changed. Yeah, even if we write, because this is like we are doing the left half. So I don't think this is, because since we are doing in order, we are first going through root left and left, root and right. Okay, so I don't think this will matter at all, even if we are breaching on the left side. And even on the right side, it won't be checked, even though it's breaching, because it's already breached on the left. Okay, so since we are going first to the left, putting that condition doesn't matter. Okay, still you can play around and let me know if I have missed something, because this is a bit confusing topic, I know that. So I hope things are clear, and I hope you got how things works in recursion. And most important topic, that what's the time complexity. So of course we are visiting all the nodes. In worst case, if we are not breaching and we are not using this recursion, this return statement and conditional recursion, then we are visiting in worst case all the nodes, right? And everything is true, like if nothing is breached, then we are visiting all the nodes. So time complexity will be order of number of nodes, and space bit tricky, but not that much. That the space will be the space used by this recursive stack. Okay, and we have seen that in worst case, the space will be height of the number of tree, right? Total space that will be occupied at a time. Okay, it's not like we have all the elements of the tree all together in the nodes. It will be just the height, because we are popping as well. So it will be order of height of nodes. But if we have recursive, skewed tree, which is just like this, only the left skewed or right skewed, then it will be same as number of nodes. So you can write as height of nodes, or also in worst case, same as number of nodes of the tree. So that's all for this lecture. So stay tuned. Please try to practice and let me know if I have missed something. And bye bye.